So let us now look at ways of achieving mode locking. My discussion is going to be semi-quantitative, uh, but I'll basically describe one active method and one passive method. So let's look at the active method, and this is by using something called loss modulation. What one is going to use is something called amplitude modulation. One is going to implement amplitude modulation of the cavity field. As the amplitude is getting modulated, one actually hopes to couple the various modes. So let me just indicate how that works. So imagine that my electric field, I'm now interested only, let's look at the plane wave approximation. Em is my amplitude, sine km for a particular mode. M here indicates the particular mode, and sine omega m t plus phi m. This is essentially the electric field associated with the standing wave within a cavity, where the m indicates a particular mth mode, longitudinal mode of the cavity. Now you see this particular object, the amplitude of this is what is being modulated. That is, I'm looking at em as some e naught, which is fixed for all the modes, and this is 1 plus epsilon times cosine capital omega t, right? So here you would see that capital omega is the modulation frequency of the amplitude modulation. Epsilon here is the index of modulation. And so for example, if epsilon is greater than 1, one would say over modulation, but typically one chooses a value which is smaller or equal to 1. So you see that if I am now analyzing the frequency components, once I plug this back into my top equation, I can analyze the frequency components of em. So essentially what I'm analyzing is this term, which is cosine capital omega t coming from the modulation times sine omega mt plus phi m, right? So this is the frequency components which I need to analyze, right? So you see that this particular product, right, which is what I have taken from the top equation, actually results in the following: that I have sine a, a difference and a sum of the two frequencies. So that is omega m t plus capital omega t plus phi m, and you have the difference frequency, which is omega m t min plus phi m minus capital omega t, right? So if you look at this, essentially what you would get is you expand this, put it back into, let me call this as equation number 1, and this relationship 2 I'm putting back in equation number 1, and what I get is my final em of t simply e naught. You get three terms. One is with the, remember that the modulation is 1 plus epsilon, so there is sine omega mt plus phi. Then there is a second term which is epsilon by 2. Here this is sine omega m plus capital omega, this times t plus phi m. And there is another term which is the difference frequency. And the whole thing is multiplied by the spatial dependence, which is simply sine kmz. So let's look at it pictorially. What I would see that in my frequency space, I have got, this is my sinusoidal wave which is at omega m frequency. Let me call that omega m. I have got another term which is shifted at a frequency which is omega m plus capital Omega, and you have another term here, right? Omega m minus omega. So once you have these terms, you see that these are spaced by capital Omega about the central frequency. They are equispaced side bands of uh, the frequency. So you see that this is what is going to be the structure of an individual mth mode within the cavity. So now let's put this idea and generalize it to multiple modes. So let me just look at three modes, right? So let me call this as my central frequency associated with, let's say, omega m, and I have another frequency. Let me call that as omega m minus 1. This is the next mode frequency. Remember that these are separated by c by 2l, and I am plotting another mode which again is equispaced, and this is omega m plus 1, right? And hence there are these series of modes which are there on either side of this central frequency. So once you modulate these fields, you see that each one generates its own sideband. So for example, you would see that the central frequency omega m generates a sideband, right, which is there, and another sideband which is there. Absolutely similarly, the omega m plus 1 field would generate a sideband which happens to be equispaced, right? And these are equispaced with these frequencies being capital omega, right? And this sideband, for example, frequency is going to be capital omega. And similarly for the lower mode, we have, so you see these dashed lines are the sidebands generated by modulation, whereas the solid lines are the original modes which are there. So you can clearly see my original set of modes had a difference of c by 2l, right? And my modulation frequency, which I can choose independently, separately, if my modulation frequency happens to be that of delta, right? Remember, delta was the angular spacing between them, which was simply uh, 2 pi times c by 2l, right? Which would be pi c by l that way. So if we choose the modulation frequency to be this, you can clearly see that at a particular frequency, the three frequencies are going to overlap. And the the most important point being, so if you look at the structure of this, you will see that the phase carried by the central frequency and by the side bands is exactly the same when you do amplitude modulation. So you see that uh, this particular frequency, for example, look at the omega m mode, this particular frequencies and its sideband, which is this one and this one, right? These two are sidebands of omega m. They are exactly in phase, right? So you see that at a particular frequency, when you satisfy this condition, right, you are creating actually variation of the electromagnetic field is happening at a particular frequency, right? For example, at this frequency, right, there are three different fields which are probably out of step. And once you have these frequencies overlap, they actually lock themselves to a common phase. So that phase is such that it now becomes common to the omega m mode, the omega m plus 1 as well as the omega m minus 1 one, right? And hence this kind of locking it propagates across the whole mode structure, and you get amplitude modulation being the mechanism of achieving mode locking. right? So this is essentially the basic idea. So essentially what one is actually achieved, each mode is strongly locked to its neighboring mode, strongly locked or coupled, if you like, to the neighboring mode. That's essentially what is being achieved by amplitude modulation. One has to essentially come up with sufficient strength for the modulation to make sure that the coupling is significant, and that is how one achieves mode locking. Now one may ask, how does one actually implement such a modulation, right? So what we are doing is you have got these modes. The modes are of different strengths. So imagine if I can modulate the loss of my cavity, right, which will essentially determine for me. Remember that the modes that oscillate are the ones where gain is equal to the gain threshold, which is the loss. So imagine if I can modulate the loss just a little bit to get these to get the individual modes to oscillate, right? These individual modes who are lasing because their gain is coupled to the loss. So by modulating the loss, I'll be able to essentially modulate the amplitude of individual modes within the cavity. So to achieve that, one way is to do something called the acoustic loss modulation. So let me quickly, tell you about that. So that tells you physically how to implement this business of amplitude modulation. So I'm looking at now acoustic loss modulation. What you are relying here is you are relying here on diffraction of light by sound waves. Sound waves are waves arising out of a density variation. So this phenomena is also called Brouillon scattering. So what you get is that uh, imagine that you create a standing wave pattern, right, within let us say a crystal. So let me show you some sort of a diagram. So you have, let's say, a quartz crystal. You're driving it with a piezoelectric crystal. This creates a density variation. So let me indicate that density variation, uh, something like this, thereby creating a variation in the refractive index. So what one gets is essentially something like this, that my light beam comes in and gets scattered because of this density variation, right? This is my light. So for example, this angle is theta, and this is where you get scattered. So we can construct from this relationship that simply tells you the relationship where in the angle at which the light beam is scattered is actually sine theta equals lambda, lambda being the wavelength of light, times 2 times n is the refractive index of this material, times the wavelength of the sound wave, right? So that is precisely where one would see this maxima. So effectively, one can do a detailed analysis and see that the variation in the refractive index of this material, the variation of this refractive index along this direction, which is x, uh, can be written down this fashion. There is some amplitude of this variation, sine omega s being the angular frequency of the sound wave, omega st plus theta. Theta is precisely arising out of this relationship, right? Uh, times sine ks x, right? So remember that lambda s is essentially 2 pi by ks, right? The usual, and my uh, omega s is basically 2 pi uh, nu s, right? And these are all got to do with the sound wave. Right. So you can clearly see now that sine omega st plus theta, if this is equal to plus minus 1, the maximum values, you will see that you will have the largest variation, the refractive index. That is where these maximas occur. Essentially strengthening of this acoustic wave or the density variation or the variation, the refractive index periodically in time, right? And if one the so this diffraction pattern itself would be oscillating, right? This will be an oscillating diffraction pattern at uh, you know twice omega s, where omega s is a sound wave. This is the period, or rather, let me put it this way. This is the oscillation of the diffractive grating, right? One has created a grating using the sound wave, right? So when the grating itself is oscillating at twice omega s, clearly you see that if I now make my twice omega s to be equal to, you know, pi c by L. Remember that was our uh, the frequency spacing between the bare modes of the cavity. So you see that this condition will actually lead to modulation of this diffraction or loss. Imagine such a medium is kept within the lasing cavity. So you say this will create essentially loss because it will diffract the beam away from the normal path at this essentially at this frequency, and thereby implement something which is akin to a amplitude variation or amplitude modulation of the electromagnetic field within the cavity, right? So this is essentially how uh, such an active method of creating, modulation within the cavity or amplitude modulation within the cavity is implemented. And if you choose the frequency of modulation sufficient as well as the index of modulation that you are strong enough for various modes and their sidebands to couple, in that situation you are going to achieve mode locking through this mechanism. So the next mechanism I want to talk about is a passive method. This is certainly an active mode locking method. This is now what we're going to discuss now is a passive mode locking, and this is done by the same ubiquitous saturable absorber that we have talked about earlier in a different context, and I will bring out the differences between the two. But one can use the same saturable absorber and essentially obtain a similar effect that we want to achieve, which is that of modulation followed by appropriate period of the modulation and resulting in mode locking. The way to describe a saturable absorber mathematically is through such an equation, which I'm saying is there is a absorption coefficient, okay, and the absorption coefficient can be saturated. Imagine it has the same saturation characteristics like we discussed earlier, right? I by I saturation. Just like the gain saturates, the absorption saturates in a similar manner. So you see that imagine you have a medium that shows this property of saturable absorption, and it is homogeneously broadened for simplicity. It's not really necessary. And I am looking at now intensity I, which is reasonably small in comparison to I saturation, right? It is not required. Just to keep our analysis simple, I can rewrite my A as some A naught, and this, because I is small, this denominator fraction is much smaller than 1, so I can as well write this as 1 minus I by I saturation, right? This is my approximate form. Right. So now let us figure out what such an absorption does to the electromagnetic field itself. Remember that my electric field within the cavity, now let me look at a simple case where I have exactly two modes, right? I have I have E1, which is one mode which has got appropriate propagation constant K1, and it is a standing wave solution. So I have got both sine k1z and sine omega t plus phi 1. And I have another mode which is E2 sine k2z sine omega 2 t plus phi 2. Right? These are my two modes which are present. Of course, we have multiple modes, considering for simplicity two modes. And you see that I can rewrite now, given that this is my electric field within the cavity, I can write down the intensity, which is what precisely goes into my absorption coefficient. This intensity as a function of Z and T will be of the following form. So let me write down the expression, which is C epsilon naught, which has got the following three terms plus a cross term, which I am rearranging in a manner that this is equal to. Now, if I'm looking at intensity, I need to average over a few periods, right? So that averaging process will lead to the following, that my sine square omega t, this will give me a factor of half. This will again give me a factor of half. And then I will simply open up this product carefully and see what I get. So essentially at the end, you can implement these relationships between these harmonic functions, and what I get is my average intensity to be of this kind, which is C epsilon naught by 2. These factors of 2 are coming from averaging, and the first term is simply E1 square sine square K1z plus E2 square sine square K2z, right? These are the two terms, plus there is a cross term which is twice E1 E2. Now it is sine K1z sine K2z times cosine omega 1 minus omega 2 t plus phi 1 minus phi 2. You see, there is another term which was the sum term, but because we averaged it, that goes to zero. So essentially, you have something like this. Now, you clearly see that I have got a sinusoidal modulation of the intensity that is already present in my system. And you see, and we already know that omega 1 minus omega 2 is indeed, you know, delta, which is indeed pi c by L. That is how these two modes were to begin with. So you see, essentially, we will now have an intensity that is getting modulated at this difference frequency. That is inbuilt, in such a passive system. You're going to have now a modulation in the absorption. There is going to be eventual modulation in the amplitude, and hence you're going to create the side bands and eventually lead to mode locking. Of course, we have taken a simple scenario of just two modes, but when you do multiple modes, the difference frequency is exactly the same. So you do get this modulation in the intensity. And remember, once I plug this back into my equation, yeah, let me call this as equation number 3. And if I just do that, then you see that I can quickly get my amplitude modulation in this system. So just a caveat. Remember, we have used the same saturable absorber as a means of doing Q switching on one hand. And on the other hand, we are looking at mode locking being implemented also by a passive saturable absorption. So what exactly is the difference between the two? So I will simply now dwell on that difference between the saturable absorbers required for Q switching as well as mode locking. One thing very clear is that in for mode locking, I need to ensure that my absorber responds very quickly to the changes in the cavity intensity. Now let's look at my equation number 3. So you see that my A, which is given by A naught 1 plus, let's say, I1 by I saturation. And imagine that this changes over to A, A naught, which is 1 plus now I2 by I saturation. This change is happening instantaneously, right? There is no lag time between the variation in the absorption from this particular value to this particular value. And this instantaneous response is what we are assuming, and hence we are doing this analysis. So that is actually sort of inbuilt in our analysis. So basically what we want is the following, that our saturable absorber, or rather there should be no transience in the absorption coefficient, and rather the transients should die out within the round trip time. So my response time of the response time of the saturable absorber should be less than uh, you know 2L by C, which is my round trip time. If we can respond faster than that, essentially the absorption will be remain constant as the intensity varies. And of course, for Q switching, one doesn't really require that there is such a short response, and a longer response time is usually tolerable when we look at Q switching. Now, if you look at the other aspect, that is, you remember in queue switching, what we want is that we want to ensure large unsaturated, gain even after the saturable absorber has got saturated. So saturable absorber gets saturated at a particular saturation intensity, but that intensity should not be so high so as to saturate the gain which is being built up in the gain medium. Because what we want to achieve at the time we switch is that we require large unsaturated gain so as to create this giant pulse from Q switching. So we have a condition that my I saturation for the absorber is smaller than the I saturation for the gain media associated with the laser. Of course, this is true for Q switching. This is a requirement. Obviously, this requirement can be relaxed when we're looking at mode locking. In mode locking, a larger value of the I saturable absorber will actually work. And when you put in an absorber, multiple times you would get, you know, uh, the pulses which are both Q switched as well as and mode locked. So you see that what you get is a series of pulses. So this profile is that of Q switching, Q switched giant pulse. Whereas if you look at the spacing between this, right, between the pulses, this is simply 2L by C. This is the kind of spacing mode locked pulses that you would get. So this is the kind of behavior that one might get when one has both, Q switching and mode locking working together. So, but basically for mode locking, remember the idea is the following. I have, for example, the cavity, I have the gain medium, and I have put in a saturable absorber here. So then what happens is, essentially I have a pulse of light, and this pulse of light is going around. So as this pulse travels through this medium, you will see that when it reaches here, you know, at this location, for example, it basically saturates the saturable absorber, making the whole medium transparent, right? And then when this pulse reaches the edge of the cavity, part of it comes out, and the rest of the pulse, begins its journey backwards. So this is, this single pulse is going around, and hence the periodicity, right, between these pulses that we get at the output. So this is what I mean. I'm just redrawing the cavity multiple times. So essentially you will see that there is very little light except for what is there in the pulse itself, and hence the output pulses come out at 2L by C. That is the period with which the output pulses will come out, because that is the round trip time of this pulse going around within the cavity. And this is essentially the mental picture that you can carry for this business of mode locking. And obviously, because we have a short pulse in time, invariably that involves that you have a large number of frequencies contributing to creation of that short pulse, and that we have seen. Thank you.